Dalton's partial pressure. A scuba diver air tank contains a mixture of oxygen, nitrogen, and helium gases. The partial pressure of oxygen in the tank is 45.0 atm. Nitrogen is 120 atm, and helium is 35 atm. What is the total pressure in the scuba tank? So in this question, we are going to be using Dalton's partial pressure. If you were to have your reference paper, which you'll be having in your ACP, we can see that our formula for partial pressure is our total pressure equals the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. So we're going to be using this formula here, so I'll be writing it. Our total pressure equals pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3, and etc. So in this question, we can see that the question is asking for our total pressure. So we are looking for PT. So I'm going to write this again. This is our missing variable, total pressure. Okay, so now I'm going to input the rest of my information. I can see that my pressure of my first gas, oxygen, is 45 atm. So I'm going to put that 45 for oxygen gas. I'm going to put this right here. Oxygen gas plus nitrogen gas plus helium gas. These are the gases that we're looking. Okay, our second gas is nitrogen. So I can see nitrogen has a pressure of 120 atm. And our third gas is helium. This is helium. So we are going to put this into our formula, 35. Okay. So if we add all three pressures of each individual gas, that's going to give us our total pressure of our air tank. So we're going to input this in our calculator. 45 plus 120 plus 35 equals 200. So our total pressure in that oxygen gas is 200 atm. Our second example will be an ideal gas. So the question says, a medical research fills a 57 milliliter container with oxygen gas to store in the lab. The gas inside the container exerts a pressure of 2 atm at a temperature of 298 Kelvin. How many moles of oxygen gas are in the container? So in this question, we are going to compare volume, or we have volume, we have pressure, temperature, and it's asking for moles. So if we look at our reference paper, again, you will have this in your ACP. Under behavioral gases, we will be using our ideal gas formula. So pressure times volume times our moles times our constant times temperature. So I'm going to write that formula here. Okay, so what we're going to do is write down our variables. Our pressure that they gave us is 2 atm. Our volume is 57 milliliters. Okay, one thing to note is that with our ideal gas formula, our volume needs to be in liters. So this needs to be in liters. To convert milliliters into liters, what we do is we write down our decimal if we don't have them, and we move it 3 times to the left to convert it to liters. So 1, 2, and 3. So this is going to equal to 0.057 liters. So we will be using this in our formula. Okay, R moles N is what we're looking for. So this is our unknown variable. And then our constant, R. Our constant can be found in our reference material as well. So under constants and conversions, you see right here that R, our ideal gas constant, is 0.0821. So we are going to be using that value, 0.0821. And lastly, our temperature is 298 Kelvin. Temperature as well needs to be in Kelvin. If they were to give us Celsius, we would convert Kelvin by adding 273 to our degrees Celsius. But we don't need to do that in this case. Okay, so now we are going to input this information in our formula. So we're going to begin here. Pressure. Our pressure again is 2 atm. We're going to put 2. Volume is 0.057. Our moles is unknown, so we're going to put that, our unknown variable, times our constant, which is 0.0821, times our temperature, 298. Okay, so we're going to put this in our calculator. So 2 times 0.057, it equals to 0.114. And now we're going to multiply 0.821 times 298. 0.0821 times 298 equals to 24.46. 24.46. We're going to round up to 47, right? Because it's 24.465, so we're rounding up that 6 to a 7. All right, times our N. Okay, now we're looking for a number of moles. To solve this, we need to isolate our N variable alone. So we do the opposite of what's occurring here. I'm multiplying 24.47 times N. So I'm going to do the opposite, which is divide. So I'm going to divide out 24.47 to both sides. Okay, so N can be alone. That cancels out. All right, and we're left with our moles on the other side. So we're going to divide out 0.114 divided by 24.47. And that gives us 0.0046. Let's see, 46 also rounds up to 47. So our answer is 0.0047 moles of oxygen gas. Okay, Boyle's gas. So a scientist drops a sample of gas in a syringe at a volume of 120 milliliters and a pressure of 1.23 atm. While keeping the temperature constant, the scientist pushes the plunger until the pressure increases to 2.4 atm. What is the new volume? On this question, we are comparing volume to our pressure, right? And this says that our pressure increased, and it's asking for a new volume. So we see that we have 2 pressures and 2 volumes. We go back to our reference paper. If we look we are going to be using this formula for Boyle's law, pressure and volume. We're going to be using pressure 1 times volume 1 equals pressure 2 times volume 2. So let's write down our variables. Pressure 1 says our pressure 1 will be 1.23 atm. And when our pressure is at 1.23, our volume is 120 milliliters. Okay. And then the question says that our pressure was increased to 2.40. So our second or final pressure, 2.40 atm. Our question is, what is the new volume? So we're looking for volume 2. So let's fill this into our formula. We're going to begin right here. So pressure 1 is 1.23 multiplied by volume 1, 120, equals pressure 2, 240, 2.40, times volume 2, which is unknown. Okay, to solve this, we multiply 1.23 times 120. Let's do that. 1.23 times 120. That gives us 147.6. Okay, on the other side, we have 2.4 times V2. Okay, all that's left to do is solve for V2. So in order to isolate this variable, we're going to divide out 2.40 to both sides. If this cancels out, we're left with volume 2 on the other side. And then we are going to divide 147.6 divided by 2.4. So 147.6 divided by 2.4. That gives us 61.5. Our new volume is 61.5. Okay, in this case, we use milliliters. That is our final answer. Our fourth example is a Charles gas equation. So we are going to read it. A hot air balloon is filled with air and has a volume of 2.57 liters. At a temperature of 320 Kelvin. As the air is heated up, the temperature raises to 376 Kelvin, while the pressure remains the same. What is the new volume of the hot air balloon? So if I look at my information in this question, we can see that we started with the hot air balloon that has 2.57 liters, so that's my volume, at a temperature of 320 Kelvin. So that's temperature. Says that the air was heated up to 376 Kelvin, so that's temperature 2. And what it's asking is our final volume. So if we look at our reference material, we're comparing volume to temperature. So we see right here, volume to temperature, right here, volume, temperature, volume, temperature. We'll be using Charles law, gas law. So let's write that down. So volume 1 will be divided by temperature 1. That'll equal our volume 2 divided by our temperature 2. Let's write down our variables. Volume 1 is 2.57 liters. Temperature 2 is 320 Kelvin. Volume 2 is unknown. And then temperature 2 has risen up to 376 Kelvin. So we're going to start up here with volume 1. So volume 1 is 2.57 liters. We're going to divide that by temperature 1, which is 320. Volume 2 is unknown, so we're going to put V2. We're going to divide that by temperature 2, which is 376 Kelvin. Okay, for this question, we're going to solve by doing our butterfly method or cross multiplication. I'm going to multiply my variable times 320. So that still stays as V2 times 320. Okay, now we're going to cross multiply 2.57 times 376. Okay, we're going to put that in our formula or in a calculator, sorry. 2.57 times 376. That equals to 966.32. 966.32. Okay. And then all that's left to do is solve for volume 2. So by now you should know that we divide because we are multiplying here. So the opposite of multiplication is division. So we need to divide out this 320 to both sides. So we can have volume below. So our final volume is 966.32 divided by 320, and it gives us 3.01. Okay. We use liters, so it's 3.01 liters. For our last example, it is an Avogadro gas example. Question says, during an experiment, a scientist observes that 2.5 moles of gas occupy a volume of 65 liters. The scientist reduces the number of moles to 1.15, while maintaining constant temperature and pressure. What is the new volume of the gas? On this question, we can see that we start with 2.5 moles. My variable for moles is N. And when we have 2.5 moles, it occupies 65 liters. So it says volume. Question says that the scientists increased the moles to 1.15. And the question is asking for our volume. So we can see that we are comparing volume to the number of moles. We use our reference material. We are going to be using this last formula. Volume 1 divided by number of moles 1 equals volume 2 divided by moles 2. So let's write that formula down. Volume 1 divided by moles 1 equals volume 2 divided by moles 2. So let's write down our variables. V1 is 65 liters. Moles 1 is 2.5 moles. Volume 2 is unknown. That's what we're solving for. And moles 2 is 1.15. Let's input these variables in our formula. So volume 1, we're going to start here. Volume 1 is 65. divided by moles 1, which is 2.5. Volume 2 is unknown, divided by moles 2, which is 1.15. Okay, so we have this set up once again. So to solve this, we do cross multiplication, or our butterfly method, as some of you may know it. So we're going to multiply V2 times 2.5. That still equals to V2 times 2.5. And then we are going to multiply 65 times 1.15. Okay, so 65 times 1.15, that equals to 74.75. 74.75. Okay, to solve for volume 2, we are going to divide out 2.5 from both sides. So we are left alone with volume 2. So volume 2 is going to equal to 4.75 divided by 2.5. And that gives us 29.9. So volume 2 is 29.9. Sorry, not moles. Liters. Liters. That's our final answer.